Hello, let's work on the second case of transition to turbulence modeling. So now we have a more practical case. This is an airfoil. You can download the image, you have the link. So this is a very large domain. So usually this is the kind of domains that you use when you're doing external aerodynamics. So let me show you the airfoil now. Let me go zoom in. So this is a 3-element airfoil. Okay, so we have the flow coming at an angle of attack. By the way, we have experimental data from this case. So when you download the data in the link, you also put this file with the references, so you can get there, leave, drag, and also we're going to compare with CP, pressure coefficient. So what we have here, the 3 elements, and the interesting thing in this case that we're going to have a laminar separation bubble. So remember in the previous case we didn't have, in this case we have it. The idea is the same, how to model, we address boundary conditions, everything. But remember that the price that you pay when you do transition models is that you need very fine measures, okay? So just to show you some results here that I pre-plot. So I will go contours and I'm plotting here intermittency and see here what we have. So here is clear to see where you have the transition to turbulence, okay? So see that here, everything laminar, and then boom, you have the onset of the turbulent flow, okay? So always remember that close to the airfoil, you have the viscous layer, so it's always laminar. So see that clear here, you see the transition to turbulence. So you are going to see when you plot friction coefficient, for instance, you are going to see that here probably is laminar, is smaller, and then it becomes larger here. So if we move here, see again, okay, so here is better to appreciate this transition model working laminar, and then you have the onset, and then becomes fully turbulent, okay? And then we move to the flaps, and the same idea, okay? So in the bottom you have laminar, so this is a favorable pressure gradient. So remember from aerodynamics, usually when you have favorable pressure gradients, stay laminar, so here is a adverse pressure gradient, it will permit separation. So the flow is coming in this direction. I think it's what we call it slide 13 or 14 degrees. In any case, you can compute it from the inlet conditions. So, and just to show how to see, so you see here that you can define, you can see where you have this separation, but also you can appreciate better those separation bubbles by plotting velocity vectors. That here I'm plotting velocity vectors. You will need probably play with the scales. In this case, everything pretty fine, but also I'm using coloring by turbulence intensity to see better. So if we look here, see that here we have the onset of the turbulence, and see that this is a laminar separation bubble. See that the flow is attached, and suddenly you have the separation, and you have this bubble, and these are these recirculation regions, very difficult to capture. You can guess that you need very fine meshes, but not only you need those fine meshes, let me plot it there, in the normal direction to the wall, but also you need it in the spines-wise direction to capture. Okay, so see that here you capture very well in the normal, but probably the spines-wise, it might be a good idea to subdivide the cells to get it well. If you want to precisely pinpoint the dimension or the reattachment point of that separation bubble. But here in this separation bubble, flow laminar, and then as soon as the flow reattach, it becomes turbulent. See that here it reattach and fully turbulent. Okay, and then if we move back this end, we're going to see probably, I think this is smaller bubble. Okay, probably it's not a smaller, but probably would be better to add more cells here to better capture. But here you see that you have that bubble reattach and then fully turbulence. And just to mention that maybe it is smaller, or you see that you didn't have that large bubble because here you have a secondary flow entering. So remember that is flow coming as an angle is passing here, and then that flow will have an influence here that it will promote will help to this flow to stay attached. Okay, so you see here, and if I plot the velocity, see that you have this jet here that it will reduce that bubble intensity. And also there will be, you can capture the other one here in the back. So let me go on and plot it again here. Okay, so here in the back you will have another bubble. Okay, you see here, this is also smaller, or probably this is a large one. Okay, so this is the idea of transition to turbulence, and in this case, more realistic. So let's go through the setup, the general one. So always I like to use this vertical approach. We define here the solver. So then viscous model, we are using this one. Probably this is the most complete one. Okay, this is the one that solves for its equations, intermittency plus the boundary layer momentum sickness, but you have different turbulence models you can play with that. Again, I'm not going to run it, but if you run, for instance, Paramaras, K, Epsilon, K, Omega without any of these transition corrections, you won't be able to capture these laminar separations models. Okay, again, just to stress it, you use this transition to turbulence models when it is important to the physics, when you want to really capture that. Okay, so we move. By the way, for instance, you go here, K omega SST, and if you enable that correction, okay, SST here, intermittency, it will enable by default also the cathode lambda correction. So as you recall, we addressed that in the production lecture. So usually when you do the transition to turbulence, those corrections, you see that they are enabled by default. You don't want to produce too much turbulence intensity and stagnation points. So we define the solver, nothing else here. So in this case also we're enabling energy equation, so nothing changed. Okay, in terms of Fluent, the equations, you will have new equations. Materials, you define your working material. So in this case we have ideal gas, okay, everything defined. And we move here to boundary conditions. So here just I want to mention that we divide the airfoil in different sections. So you see that you have top, bottom wall for that flaps and airfoil, and we have one single boundary condition. Okay, so usually this is a very powerful boundary condition, a far field, pressure far field that is only available when you're working with compressible flow. So you need to enable energy. So you use it when you have large domains, like in this case, very large domains. So basically what you are going to define this boundary condition, okay, you only will give, it will ask you the Mach number. So you see that Mach number, you give your flow direction. So if I will recall, corresponds something about 13, I don't recall. And again, you give your boundary conditions for the turbulence model, in this case intermittency. Remember that intermittency level at the inlet, put it 1, a standard practice, or something different from 0, okay, something large, but usually put it 1, and then you give your turbulence intensity level. And what is going to happen also, remember the decay. So from the inlet to the airfoil here, there will be some decay, so you set a level here, and then you will get some reference turbulence intensity there. So in the documentation you have how is that computed. And thermal, okay, we have temperature, so you define your thermal here, your temperature at the inlet, and that's all. Okay, so this boundary condition will deal, is the flow is entering, is entering, is going out, is going out. So you need, everything is computed automatically by Fluent. Then we move, okay, and we go to solution. Again, we are using the coupled solver, which is the most robust one for a steady solution. But feel free to play with different schemes, okay? Then report definitions. So remember that do not rely only on the residuals to assess the convergence rate. Okay, I'm repeating this a lot because it's true. If you're a newbie in the CFD, usually you will rely in these residuals, which sometimes they are not telling anything. So be careful, define so interference quantity. So in this case, we're computing CL, CD, so an average velocity, a maximum Mach number. Okay, so just click there and you will see residuals, you define your residuals. In this case, see that I put it very small because this case is converting really fast, so just to let it run for a longer time, but also you can decide, okay, actually they are disabled, okay, the convergence monitors, or if you want, you can also check a convergence condition for any CLCD. We have done that in the production, in the previous case with the production limiters. And let's initialize. Okay, we go from far field, initialize. Okay, and at this point, calculation activities, in this case we're not setting anything. Remember that sometimes when you are running large cases, okay, it's a good idea to auto-save the solution every given iterations, okay? And let me move. Now we can run, okay? So let's spray calculate, put a number of iteration, and let's see what we have. Okay, so let's see the residuals. You have all your monitors. So by the way, I use standard initialization. Remember that you can also use the full multi-grid iteration initialization, that it might be better for this case. Okay, so you can play with those different initializations. So we have all our residuals here. Okay, so K omega, intermittency, red theta, X velocity. So you see that also using this transitional model is adding more, it's making your computation heavier. Okay, you're resolving 2 more equations. Our lift coefficient, our drag coefficient, our average velocity. I don't recall if it's in the outlet or in a point, but in any case, monitoring one quantity, and the maximum Mach number in our domain. So let's see what we have. Let's wait a little bit, and then we do another post-processing. Okay, we're back. So I run the case like 700 iterations and see that all my residuals, my integral quantities stabilize. So drag, lift, probably might be necessary to run a little bit just to see what happened with drag. But let's say that we can stop it. And what I just stress in continuously is you look at this, probably you will say that you haven't converged whatever, or will take whatever is you want to get this one to fall below, let's say 10 to the minus 3. But your true indication is this one. Okay, see that this one, they are not oscillating, so you can take that this is a, you can say that this is a converged solution. One thing that you can play around with the initialization type. So when I launched at the beginning, it was standard initialization. This is a run using what I'm showing here, using the initialization using full multi-grid. So it's much faster. If you use the standard initialization, it will be slower. You will see some larger oscillations, and you will need to wait a long time to get the residuals stabilized. But pretty much the same. So you can also play around with the initialization, and you can see the influence of initialization and the convergence rate. So we have the solution, drag, also the velocities, Mach number, minimum, maximum, your domain. And so at this point, we can do the post-processing. We already did it at the beginning, but just to show again. So we have here the velocity. Okay, so pressure, so static pressure. Then you can check your velocity. Okay, velocity field. You can also get access to Mach number. You have it there. Okay, so there are some peaks there. Here as expected, and turbulence quantities you can access. By the way, also you can access density. Okay, remember it's compressible, so you have density variation, you have the temperature field, so you can access all your variables, plot your velocity vectors. And let's do the post-processing here, XY plot. So here, let me plot, okay, the wall shear stresses at the flat, okay, here in the back. Okay, in the top wall. So as you plot this one here, so you remember the flat plate that we have this behavior. See that it's from here, then it's going down. So see that here, this is a laminar solution here, and then you have the onset, boom, here, and it becomes turbulent. And this is very similar to the previous one. So if I plot now for the top, also I will should have something similar. Okay, see here laminar, and then the onset on the turbulent flow. And as you go to this slat, probably it's a little bit trickier to identify that region, but probably will be this one here. Okay, boom, and then goes. Okay, but as you see, you have those similar behaviors that you have in the flat plate. And the final part, just to do, because we have also in this case static pressure and pressure coefficient. Okay, and let's plot everything in all the surface. Okay, so you have the slat, airfoil, and flat. But we can load the data there. You have this one. and we can compare. And you see that this is a remarkable good agreement, okay? This is a complicated geometry transitional model, and see that it matched very well the experimental results. Okay, so I think this is all for this case. My advice here is just play around with initialization. You will see the influence. Also, you can play around as we did with the flat play, but probably it's better stick with the flat play, which is because it's fast. This, as you see, is a little bit slower. Depending on the initialization, you might need to do 500, 600 iterations. Okay, so but again, you can play, okay, here in the intermittency value, tones intensity, initial conditions, okay, and also you can go with the numerics. So that's all for transition to turbulence. In the next tutorial, we're going to address a simple case, the flat plate, with all this knowledge that we have. We're going to set up the simple boundary layer in a flat plate. So hope you enjoy it, and see you next time. Bye.